All right, any other questions besides that one with FS new thing that we talked about? All right, so I want to talk one more time about the quantization noise that we have, and before we move on into data converter SNR, and I want to hopefully I kind of whizzed through this last time, but what we're going to do is we take some analog input slow ramp, and that goes to an ADC, and then we get some. How's today's homework anyway? Too easy? All right. You laugh. I don't know. You guys aren't complaining enough. That's why. All right. Back. And then I take my output. And remember, it did this. And the thing is, we put the slow ramp in so that we would get kind of a real good representation of the input. In other words, it's not moving so fast that we're going to skip LSBs. It's going to be slow. So then we take. So which one of these is clocked? Yeah. We take that input and we feed it into a adder, and then that comes out, and we say this output, the difference between the input and the output is, yeah, the quantization error. Okay, and we did a sim on this last time, and if you recall, what the sim looks like is the following. It's with time, it's a waveform that looks something like this. And this is plus 1/2 LSB. And this is minus 1/2 LSB. And 1 LSB is what? Yeah, Vref plus minus over 2 to the n. When does this equation fall apart? Yeah, for 1 bit, which we're going to use a lot in this class. So for 1 bit, what is 1 LSB? Yeah, just Vref plus. Okay. So if I take a look at this, this is the error. This is the quantization error. And I want to answer, or I'm going to try to answer two things here. Remember last time we developed the idea that we have some analog input and we'll get some digital output, which is some number of bits, but we're going to add some error to this analog input. So we're going to treat our ADC as a noisy block. Does everybody agree? Follow that? So the question is, this is the shape of my quantization noise. I'm going to determine the RMS value of that. Now, I'm going to determine the RMS value, but that doesn't tell me anything about the spectral characteristics of the quantization noise. But let's determine the RMS value of this, and from circuits 1 or maybe circuits 2, if you look at that, what we can do is we can call the mean squared quantization error, which would be the RMS value squared, is the average over this period t, and remember when for a sine wave it was the peak over root 2. Here we're just taking the waveform and we only need to average it over 1 cycle, because when we go to 2 cycles the time doubles, the average amount of power goes up. So we just look at 1 cycle, and you remember that from circuits. We integrate from 0 to t, say from here to here. And if you look at this equation, the y-intercept, or I guess this would be a better spot, is positive 1/2 LSB. And the slope is 1 LSB over t times t and then you integrate that with respect to dt. And if you do, what you end up getting, what's the only term in here that's a function of time? The second part, and it's a trivial integration, so you end up getting 1 over t, 1/2 LSB times 1/2 LSB minus, not this one. Oh yeah, times t. Thank you. I'm getting a little ahead of myself. I'm trying not to skip to the answer here. So plus 1/2 LSB over t times t squared, evaluated at 0 and t. Does everybody agree with that? And if we do that at 0, both of these are 0. At t, the two t's cancel. And here it's t squared, the t squares cancel. And so I get 1/2 LSB minus, wait, what do I get? I get, what is that? Yeah, so let me not skip it. It's 1 over t times 0, 0, and then this would be t over, or t times 1/2 LSB. And this is minus, let's do minus plus, and this would be 1/2 LSB times 1 over t times t squared. Wait, I've got some issue here. What's that? Because it's, oh no, that's wrong. It'd be minus 0. This would be plus. This would be minus. And then this cancels with this, and this cancel with this. Wait, I'm doing something wrong. Oh, I didn't do the square part. Ugh. All right, well, anyway, it's in the book, and the answer is 1 LSB over the square root of 12, or over 12, 1 LSB squared over 12, or I'm going to just write it on this. The quantization is V quantization error RMS equals VLSB over square root of 12. Okay, so this is an RMS value, and of course it assumes the input's moving, and it's the average value of the RMS signal that I add to the input, but it doesn't tell me anything about the spectral characteristics. And before I move on, this equation we're going to use when we talk about effective number of bits here in a moment. But before I move on, I want to rederive this another way. So when I look at this over time, there's no probability that the error, the probability that the error is 1/2 LSB is no different than the probability the error is 0, and the probability is minus 1/2 LSB. Is everybody, the probability is equal? So I'm going to write the probability density function. And again, this has nothing to do with spectral characteristics, as looking like this. This is the PDF. And so it's a constant probability, and this is the quantization error. And what are the range of the quantization error? Yeah, minus 1/2 to plus 1/2 LSB. What's the average? Wait, what is the average? 0, right? And that's the reason we shifted the quantization error, okay? All right. Any questions? How's that homework looking there? All right. So what's, just as a sanity check, what's the area of the probability density function always equal to? Yeah. So this value from here to here is 1 LSB, so this has to be 1 over an LSB. And so if I want to calculate the RMS value of the, now here's something we're going to use over and over again. For a average is 0, but what is the, if I want to determine the RMS voltage of this, what is that equivalent to in probability speak? Well, the variance would be the mean squared, and then the standard deviation would be equal to the RMS. So I'm going to write the probability quantization error here is equal to, well, the variance, I should say, which is, it's kind of unfortunate they use this language, but for us it's the mean squared, and then the standard deviation is the, well, yeah, but it's also square root of the variance, and that's equal to the RMS, root mean squared. Okay, everybody probably knew that, but we'll write it out anyway. And so we integrate this to find the variance from minus 1/2 LSB to 1/2 LSB. And the rho, which is the probability density function, this thing, which is just 1 over LSB, times the quantization error, this axis, times dq. Make sure I don't forget this squared again. So just to repeat myself, so we know why it's, these are the limits. What is rho here? 1 over LSB. This we could write as x. This we could write as x. So what is that equal to? Everybody agree with that? And then when we plug it in here, what we get is we get 1 LSB squared all over 12, or an RMS value of 1 LSB over root 12, which is exactly what we got before in this situation. The RMS is VLSB over root 12. Okay, so what I'm going to do before I talk about how this varies with time, or what the spectral characteristics look like, so I'm going to talk about effective number of bits. Okay, question?
Yeah, so does that VLSB or square root of 12 tell you how much of your signal's lost to noise?
No, it just tells you what's the RMS value of noise you're adding to your input. So here, it's telling you what's the RMS value you're adding. That's what I'm saying. You're taking and you're, okay, I got an RMS value here, I've got some analog input here, which I'm going to demonstrate right now, and I'm adding an RMS signal. It doesn't tell me what the spectral characteristics are. You know, is it this a DC or what? It's just an RMS value. It's just a power, if you will. Okay. Okay. So I want to put together a. I want to put a test bench together, which, if you want to follow along on page 173, and so what I'm going to do is I'm going to take my ADC and I'm going to put in an input here, which is got a peak value. So this is VP sine of 2 pi ft, some sine wave coming in. And so its RMS value is VP over the square root of 2. Does everybody agree with that? Then I've got my bits coming out, and I'm claiming that this adds an RMS value of 1 LSB over square root of 12, which is Vref plus minus Vref minus all over 2 to the n. Okay, so if before I go any further, if I want to maximize the signal to noise ratio, what do I want to do with my input here? Yeah, I want to make it as big as possible, because then I get the, if I put in here, a tiny little signal, then my signal to noise ratio is going to be small. So I want to make this as big as possible. So if I have a sine wave coming in here, I know the maximum the minimum I can go down to is Vref minus, and the maximum is Vref plus, and it's right around Vref plus minus Vref minus over 2. So what is this peak amplitude here? Okay, what's the difference between the two? Vref plus minus Vref minus goes up the same amount as it goes down. It's swinging around the common mode. So what's this peak voltage in terms of Vref plus and Vref minus? Yeah, it's just Vref plus minus Vref minus over 2. Nothing challenging. Okay, just as a sanity check, what's this delta here? Yeah, Vref plus minus Vref minus. And I'm saying, okay, I want to go up by this amount and down by this amount. Okay, so what's my RMS input? Is Vref plus minus Vref minus all over 2 times the square root of 2. Yay? So then my SNR is equal to 20 log, putting it in dB, of my peak input, which is Vref plus minus Vref minus all over 2 root 2 divided by 1 LSB over square root of 2, which is Vref plus minus Vref minus all over, oops, I should put square root of 12 here to be correct, 2 to the n times the square root of 12. Is everybody yay? You guys were probably like, he left off the square root of 12 there, weren't you? Alright, so then these cancel, and I go to the next page. You guys sure you don't like PowerPoint? Imagine how fast I could go if I just, and on this page, PowerPoint. Alright. I think PowerPoint would be great. I could carry a thumb drive to class. 20 log of 2 to the n times the square root of 12 all over 2 times square root of 2. Any questions? Alright, so let's simplify that. Wait, before I do that, let me make sure I got the same thing in the book. It's 2 to the n square root of 2. Oh, I did. Okay. So then I'll write a little bit longer here. So this would be 2 to the n minus 1 times the square root of 6. And so, whoops. Boy, I'm just really blowing it, aren't I? And so I can then, whoops, I better write it like this. And so then I can write, this is, we'll write it like this. I'm going to be verbose here because this is important. It's actually used a lot in industry. Okay, so I'm going to write this as 2 to the n minus 1 plus 20 log of the square root of 6, and that's equal to n minus 1 times 20 log of 2 plus 20 log of square root of 6. And let's go ahead and get out the old calculator here, because this is used so often. Well, we probably know what 20 log of 2 is from memory. What's that?
Almost a 6.
20. Oh. Oh, I did. I'm getting senile. That's, I think, from not taking any breaks. All right. Because that's the most important part of the day. All right, so that's 0.3 times 20. And so that's 6.02. So I'll write that as 6.02 n minus 6.02. Anybody disagree? And then 6 square root times 20 equals, and 6 square root log of, and then times 20 equals plus 7.78, and good enough, and minus 6.02 equals 1.76. What? Okay, so this is my SNR. All right, so let's talk about this for a moment. So what are the units here anyway? dB. So if somebody says, I need roughly 60 dB signal to noise ratio, how many bits roughly data converter do you need? 10. So when I'll go through this, well actually I can just point it out real quick. If you look at this discussion on dynamic range on the bottom of page 177, it's similar to this, but basically your dynamic range is roughly 6.02 n. So if you need 60 dB, you need roughly 10 bits, okay? Ideally, this tells you if the data converter is perfect, this tells you what your signal to noise ratio is. Okay, so question is, and this only occurs for full amplitude inputs. If you reduce your input amplitude, your signal to noise ratio is going to drop, and we're going to talk more about that in a moment. Now, what are effective number of bits? If I measure the signal to noise ratio in a data converter, and let me tell you what I would do. I would take my output of my ADC and I would do an FFT on it, and I would get some spectrum, and of course I get something that looks like this. It comes through, right? And I'll go through this more in a moment, but if I remove this tone and I go up to the Nyquist frequency and I add up or I sum up the power in the spectrum here, this gives me my noise. If I then take whatever the power was in my signal and divide it by this noise, I get the measured signal to noise ratio. I can then plug that in here and I get the effective number of bits is the measured signal to noise ratio. Again, I'm going to go over this more in a moment. Minus 1.76 all over 6.02. So this tells me if I measured, if I had a 10-bit data converter, ideally I get roughly 62 dB SNR, but then I use it in the field and I put in a tone and I measure the signal to noise ratio and I get 48 dB, then my effective number of bits is roughly 8. It's not 10 like the data converter claims. And this is used all the time. Does everybody follow that? So let me repeat one more time. Ideally, I get my resolution, say 8. Then I'd measure a signal to noise ratio then my ideal signal to noise ratio is 50 dB. 8 times 6.02 plus 1.76. If I put in a tone and I measure the signal to noise ratio, I'm going to do this in a moment, and I remove the desired tone, I can estimate or I can calculate what the noise is here by adding up the terms. That's measured signal to noise ratio. When I plug into this equation here, gives me my effective number of bits. So if I were to put in, let's make it easy on me, 37.76. I subtract 1.76, I get 36 here. I get 6 here. That's 6, so I get 36 over 6, or I get 6 bits effective number of bits. Is anybody, of course I don't expect you to know how to measure the signal to noise ratio. I'm going to cover that in a second. Any questions on the usefulness of this equation?
Why do they use sine wave fitting more than they use this technique to do effective bits?
When you say sine wave fitting, what do you...
They fit a sine, so it's in the time domain instead of going in the frequency domain.
I don't know
Okay.
what the error, what that particular situation is. All right. My guess is in that case they're putting in lots of sine waves and looking at the difference between the measured point and the ideal point, and that difference is an error. Then you take that error and you sine it up, maybe for a slow sine wave or even fast, and do it over many cycles and get an RMS value for the noise. Then it automatically removes the tone. And so then it's trivial to calculate the power of the tone. That's what you put in, and then you've got the power that you're putting in of the noise, and that gives you the measured SNR. Then you plug it in here and gives you the effective number of bits. Okay, any questions? Very important, very used quite a bit in the real world. Okay. So what I want to do now is I want to talk about the spectral density of the quantization noise. So I'm going to go back a page to page 169. Now that we've gone through two ways, we used the probability density function, and we used in the time domain just looking at the quantization error and looking at the RMS value there. And we went forward and said, well, where would we use this? And we used it in calculating the effective number of bits. I want to go back now and talk about the spectral density of the quantization noise. And so before I do that, let me just say that we're going to make an assumption that all of the quantization noise falls between DC and the Nyquist rate. In reality, there's going to be quantization noise that's beyond the Nyquist frequency, but it's worst case to assume it falls all within the frequency band of interest. So all that stuff that's higher frequency, we're going to assume it's not there, and all the noise is in our frequency of interest. Okay? All right. So what that means is, and I'm going to do some sims, and we're going to look at how this theory holds up. So remember, it's a theory that we use for modeling things. It's not a precise thing. So what I'm going to do is I'm going to write the spectral density of the quantization noise as VQE of F, and I'm going to try to explain this. If the units are funny, hopefully it'll make sense the way I explain it, but when we do advanced analog and we do noise theory, the units make a lot more sense. So the units here are volts per root hertz. And so what this is when I measure the power in a signal, the power is it's normalized to a resistance, it's volts squared over some bandwidth. Okay, so I have a bunch of sine waves in some bandwidth. I add up the power of each one. That power in that bandwidth is the power spectral density. And I'll talk about this in more detail in a second. When I take the square root, this is called the voltage, and you can get your spectrum analyzer to display either one. Voltage spectral density, but it's just a squaring function. This one, the reason it's power, you assume you know what the resistance is, okay? Here's what we're going to do. Okay, so I'm going to do this. Make sure you follow this, all right? So I assume this is the spectral density of the noise. And I'm going to talk about where this falls apart, and you actually have a homework problem on this. But for now, I'm going to assume everything's random. The noise is nice and distributed throughout the spectrum all the way up to the Nyquist frequency of F sub s over 2. Okay, so before I go any further, I want to just put a triviality out there. And I want to say remember, this is just a bunch of sine waves, right? So I want you to tell me if I want to estimate the RMS value of two sine waves. So I'm going to call these two sine waves. This one's at a frequency F1, and it's got a peak value VP1. And this sine wave, let's put it at a different peak. It's VP2, and it's at F2. And I want to write the RMS value of those two sine waves. Now, of course, here I'm not drawing the arrows, I'm drawing points, and I could do that here with just 2 points. Here I only have 2 points. Here I have a bunch of sine waves from DC to F sub s over 2. So I want to know the power in these two sine waves. Now, this is a trivial question, but I want to make sure you have it in your mind when I go back up to here. Okay, so the way I do it is I write the RMS values for each of those sine waves. So the RMS value of this is VP over root 2. The RMS value of this is VP2 over root 2. Right? But I can't add the RMS values, I can only add the powers. So then I'm going to go back and I'm going to write the powers as VP1 squared over 2, and this one as VP2 squared over 2. Okay? Then I'm going to say the total power is equal to VP1 squared over 2 plus VP2 squared over 2, which I'll just write as VP2 squared over 2. Then the RMS value of these is then the square root of VP1 squared plus VP2 squared all over 2. In other words, it's the RMS value is not the sum of these VP1 over root 2 plus VP2 over root 2. Has everybody got that? Because I can't take the, I mean, this is the, when you take the square root of this, it's not VP1 plus VP2. Please don't do that. That's like 9th grade algebra mistake. Okay, does everybody follow this? Okay, so now I could rewrite this as summing from 0 to infinity the powers of each of these sine waves. So I would write them as the powers, which would be v squared of f df. Does everybody follow that? Okay, so this is for a one-sided spectrum. It would be minus infinity. Actually, I need to do it for 2. So we could just do minus infinity. All right, for two-sided, I'm just doing everything in one-sided. If it's one-sided, we could go 0 to infinity. Does everybody understand how I got my little elongated s here that sums up this one plus this one? And that's, I'm doing the same thing here. I'm just writing it as an integral. Nothing scary. Yay? Okay, I'm hearing crickets. Am I boring you? Yes? All right. So, here's my, going back up here, here's my quantization noise. I know the RMS value of this is equal to what? So the power is that squared. And so what I'm going to write this as is the integral from 0 to fs over 2 of vqe of f squared df. Does everybody follow that? And if I do that, and I look at what vqe of f is, I end up getting VLSB, it's a kind of a trivial integral, VLSB over square root of 12 Fs, where the units here are volts per root hertz. And then the power spectral density is VLSB all over 12 Fs. Okay, does everybody understand what we just did? So if I ask, what does the power spectral density of the quantization noise look like? I assume it's band limited between DC and F sub s, which is the worst case because all of the noise falls in my desired frequency band of interest. I also assume that my input is busy and the quantization noise is random. Then there's no reason that I'm going to have one value more than another or one frequency more than another frequency in this band. Does everybody follow that? Okay, so now let me tell you where this falls apart. Okay, let me see if I have an example here first. Yeah, let's look at figure 514 because I want to do an example where it falls apart. One simple example, and I think, as I mentioned, you have a homework problem in this, is when you do coherent sampling. Coherent sampling is a simple name for meaning that your input sine wave is at a frequency locked to the sampling clock. So what you do is you hit the same points on the sine wave over and over again. Okay, a simple example of coherent sampling is if I put a DC signal into my ADC. I could get zero quantization noise if I put it right on the border where it's, right at the happy spot there. Or I could get a quantization noise which is full 1/2 LSB or minus 1/2 LSB, and that's considerably different than the quantization noise that I calculate as VLSB over root 12. So if VLSB was 1 millivolt, I could put a DC value into the ADC, and I would get out. I could get up 1 LSB noise out, or minus 1 LSB, or I could get 0 out. Does everybody follow that? So let me ask you a question just to make sure I assume everybody's following. If I put a DC signal into the ADC and I ask you to sketch the spectrum of the quantization noise, not the level, just the spectrum. I'm assuming everybody knows that it can range between 1/2 LSB and minus 1/2 LSB. What is the spectrum of the quantization noise when I put in a DC level? Yeah, impulse at DC. It would just be right here. It doesn't look like what we just derived. There's nothing magical here. It's just a model we're going to use throughout the class, the remainder of the class, to model quantization noise. Any questions? If I put in a tone that's locked where I'm hitting the same points over and over again, so I look at the spectrum, I'm going to get an output which has tones. Okay, here I would get, if I hit, let's say I hit it, this is supposed to be flat like this. If you remember your basic signals, you'll get out first, third, fifth, 7 harmonics of the input sine wave because it's a square wave. You're not going to get a nice spectrum, you're going to get out discrete tones. Any questions? So what I'm getting at, again, nothing magical. Model has limitations, won't work all the time. Okay, so let's go look at figure 514.
Is that the reason why they want you to use the coherent frequencies when doing effective bits testing?
If you use a coherent frequency, you can get well-defined tones. If you get well-defined tones and you have enough of them, okay, I'm going to say this, hopefully it'll make sense. When you do the FFT, you have a window, right? So when you window the FFT, if you use tones and they're discrete, you don't have bleeding of your bins from one bin to the other. They're isolated, and so then you can get a better estimate. When you have something that's all random and you do the FFT with this particular window, the tones bleed into one another, and then you don't get as good a results. Does that make sense?
It's mentioned in the IEEE standard to use that, and it says that the time domain that if you follow the coherent frequency, then you get an odd number of cycles in the time domain. That's kind of what you're aiming for.
Yeah. Well, you want to make sure that you start and stop with long periods so that you have really well defined so you can get your errors correctly. That's a little bit more in depth than we're going to go in this class. All right, so let's go over here and extract. And I want to spend a minute or two on this because I want to make sure we feel good about this. 514. So here, I'm going to run the sim, and let me see, do I have error here? Okay, so I want to actually, let's run it, let's not. We're running out of time here, and we got to make sure we have time for the quiz. So the sample and hold here, I'm doing it. You can go into the data if you output the data, and there's some programs at CMOS EDU for reading the data with MATLAB, but then you can trivial zero out the components. Here I'm faking it with a sample and hold. There's other ways of doing it. You can take the spectrum and subtract the tone with the overall RMS, but if I hit run, and then I go view, oops, got to select the right window. That's view FFT and quantization noise, yes. And then I'm going to limit the spectrum. I'm going to first go just to 100 megahertz. Okay, so the key point here before I hit, oh, I got to hit MEG, don't I? The key point here is Well, it's really small, but you see it's not magic. Our assumption the quantization noise is band limited DC to the Nyquist isn't accurate. I mean, it's the noise is still going out here. Okay, so I'll hit OK. And I say, okay, my Nyquist frequency's right here. You can see, okay, with 70 dB, if we're down at 90 dB over here, that's a factor of 10 lower. So you could argue, okay, well, there's going to be error in what I estimate, but I want to estimate what the quantization noise is here. And so I'm going to reset this to 50 megahertz. And then I'm going to measure the value. And so I measure 67 dB. What is that? Okay. All right. So I measure 67 dB. So I want to write that in terms of millivolts. Okay, and I'm going to do that on purpose. Before I do that, so let's just say 67. And remember, we're getting rid of some of the spectrum here. So if I do 67 dB, so minus 67, 67, change sign, divide by 20 equals 10. 67, change sign, divide by 20 equals, and then 10 to the x is 0.44 millivolts. Let's just say 0.45 millivolts. And I go back, so we can, here, let me write that down in case I forget, 0.45 millivolts. And I go back and I ask, all right, that is, okay, so what is that? What did I just write? RMS quantization noise, right? So I'll go, oh, come on. What's going on here? Well, hold on. No, it's 0.45. Okay, let me get this back. Okay, so what is that equal to in all the stuff we just derived? The RMS value. So this is where all these things are pretty useful, but there's so many equations you tend to get lost in forest for the trees kind of thing. What is that? Right? So then we go back and we say, all right, so we got 0.45, and it's in millivolts, times 12 square root equals, and we're at 1.55 millivolts. So VLSB, 1.55 millivolts. So I go back now and look at the circuit, and it's going to be off a little because, remember, I'm throwing out the higher frequency noise. And I say, all right, I've got VDD is 1 volt, I've got, or VREFP is 1 volt, VREFM is -1, and I've got a 8-bit converter. So what's the ideal LSB? Yeah, it's 1 over, what? 1 over 2 to the 8th. Yeah, 1 over 256, which is, what is that, 2.5 millivolts. And you can see, well, wait a sec, if I used a wider spectrum, I'm going to get closer to this. Did I lose anybody there? Did I lose everybody there? Okay, so any questions on how I calculated 1 LSB? It's 1 volt over 2 to the 8th. So that's 1 divided by 256. Oh, it's 3.9, sorry. Roughly 4. That's why everybody looked. So it's roughly 4. What I did with looking at the spectrum and adding everything up was I said the RMS value of the spectrum, and how did I do that again? Let's go, I'm just going to leave it at 100 megahertz this time so we get a different value. How did I calculate the RMS value of that spectrum? Control, left click, and it's 67 dB. Oh wait, that is the peak value. How do I get just what? Let me hit linear. Ugh. And then control left click. It says, wait, no, let me see. I put notes on here because I always forget. Go to FFT, press OK. Normally it says what the RMS value is. Let's try shift. Nope. Nope. Reference 4. What's that? I've tried it already. Yeah. Here, let me go look at the by pressing control and left clicking on the plot label. I tried that. Let me oh, you know what? And I went over this in the book. Let's actually look at the book. I don't think it lets you do an RMS value for the spectrum. I think what you have to do is fake it. Here you can do it. If we go hit run and look at this and then you know, press what the average RMS value is following the directions, and I remember now. If you go look in the book, here's the example we just looked at, and the RMS, it's not too far off, but here's how you estimate looking at the spectrum and the 1.13, and there's a comparison there. Okay, so looking at that, how did we get rid of the tone in the spice? How do we get rid of the tone? Because we can't look at the RMS value if the tone's there. I mean, we could in this spectrum, obviously, because if there's a tone, we're just saying, oh, it's about right here, and that's what the level is. How do we get rid of the tone in spice? Used a sample and hold, and then you subtracted it from the output. This doesn't work in a real simulation with transistors because the delay through here doesn't match the delay through here, so you have to put a, and there's some examples in the simulation, you have to put a delay here to try to max, or to try to set so they match. Alright, so read that section. We went over everything. I want to cover one more topic before we take the quizzes, but before we do, does everybody confused on effective number of bits and signal to noise ratio and noise and all that? I mean, there's lots of examples in the book, so hopefully it's not too bad. Alright, so let's go. I want to cover clock jitter, or try to at least get going on clock jitter. We won't get through it today. But it's a similar discussion to the quantization noise, but I'm going to go at it with a real, this is a very big deal in modern technologies, and we'll see why. So let me explain it qualitatively first. So here's the problem. I've got a sine wave that's coming in, and the sine wave will write as, let's be consistent, stay the same old thing, VP sine of I'm going to just write as 2 pi Fn times t. Do it a little bit different than the book. Okay, so when I go and my ADC clock comes in, I take a sample right here. Ideally, I hit it at the precise value. But if the clock has jitter, what that means is the clock edge may be here, but if there's jitter, it may be over here. It may be here. In other words, the clock edge is moving. And in oscillators, they call that what? What do they call? No, when the edge is, when the frequency is not perfect. Phase noise. They call it phase noise. It's the same thing. And it's just not the exact same frequency over and over again. All right? It's moving. Does everybody understand the idea? You're not hitting it because the clock is moving back and forth. You're not hitting it in the right exact spot. Okay, any questions? Now you might say, well, it's really tiny. Well, you're going to say it has to be tiny in order to... Okay, so before I go on, do you think that clock finite rise time would also be an issue here? If your clock is a rise time that looks like this instead of sampling, if it's doing this, can't you see it's going to give you the same problem exactly where you hit on there? If you're clocking here, you sample there. If you're clocking there, you sample there. Does everybody see that? Okay, before I move on, any questions? So now I got a question. Why did I pick this part of the waveform? That's where the slope is the highest, right? And then which frequency is going to give the worst case? What input frequency? If I put a DC in, is that going to be an issue with this clock jitter? No. So the highest frequency will be F sub S over 2. So I get the worst situation when I get a peak amplitude and I get the Nyquist frequency, because then it's screaming past there as fast as possible. Okay, so what I want to do, I'm going to find the slope here by taking the derivative of this, and I'm going to plug in F sub S over 2. So I get the derivative with respect to time of Vp, and this is my peak. It's the peak amplitude that I have coming in. The bigger, the worse this problem is, times sine of pi F sub S, so the 2's cancel, times t, which is pi F sub S cosine of pi FST. What's that? Times what? Oh, yeah. So if I look at this, I said, if I'm over here, it's not moving too quick. Clock jitter, if I sample here versus here versus here, it's not as big a deal as if I'm up here. And just a little bit of jitter causes problems. And so if I want to sample right here in the sine wave, that would correspond to a cosine, because I take the derivative when the cosine's at its peak, right? So I would set this time so the cosine goes to its peak value of 1, and I can write this term here as Vp pi Fs. Okay. All right. So I ask, all right, well, I'm going to approximate this derivative as what's my error in sampling. With regard to the clock jitter, and I'll call this del Ts. Okay, and so what I'm trying to do is I'm trying to say, well, if I have a clock and it's moving by, let's say, 1 picosecond, okay, not very much, how does that influence the sampling error if I only move 1 picosecond? Now, if you have a 10-bit data converter, you might have a millivolt or less resolution, so 1 picosecond in a fast-moving signal could be a lot, okay? So we want to quantify that. And so if we want the error, I'm going to go up here. If I want this del Vs, del T to be less than 1 LSB, so I want my error to be less than 1 LSB. So how do I write del Vs, the error in the sampling? I'm a broken record. What does that mean? That's slang. What does broken record, I'm a broken record, mean? I'm repeating myself. So what's del Vs? I want it to be less than 1 LSB, so I'm going to put it as 1 LSB. Right? Want that error to be less than 1 LSB, so I want that to be, this error, to be less than the Vp times pi Fs. But what's Vp for the worst case? Yeah, it's Vref plus minus Vref minus all over 2. Anybody not following? Anybody following? Okay, so then I go All right, so the Vref plus and the Vref minus cancel, and I get 1 over 2 to the n ts less than or equal to pi fs all over 2. Oops, I think I got a mistake here, because if del Vs goes to 0, del Ts goes to 0. If that's finite and that goes to 0, then this should be greater. Got to flip this around, because we want del Ts to go to 0, so then it goes to, I think that's right. All right. And then solving for del Ts, I get del Ts has to be less than or equal to 1 over 2 to the n times 1 over to the n. Wait, I got a factor of 2 here. I think I used 1/2 LSB in the book instead of 1 LSB. Oh yeah, I did use 1/2 LSB. So I'll put that in. So this will be multiply top and bottom. So this would be -1. And this would be pi fs. And this is for 1 LSB error. And book used 1/2 LSB, so this term is 1 over 2 to the n. Okay, so any questions on that derivation? So I made a table here just to give you an idea of what the jitter would be in a clock. Okay, so let me ask, before I even move on and show you that, let's say that I've got a square wave that's going into my scope. That's from an oscillator you designed, and you want to try to measure the oscillator's jitter. Okay, so if I trigger the scope right there and I look at that edge, how much jitter am I going to see? Wait, think about it. I trigger the scope on the rising edge right there, and then I zoom in there and I look at what the jitter is. It's not going to be anything, right? I'm triggering it on the thing that's supposed to be moving. It could be moving all over the place, but I'm not taking a trace till I cross that point. I have to look at this edge to see the jitter. Or I have to take an external trigger and then lock to this somehow and look at the jitter that way. Does everybody follow that? Because if I'm this, where I trigger says, hey, tell me where to look, tell me where to look. Well, it's telling me where to look every time. That's not changing because I'm waiting for it to tell me. So I go to the falling edge and I look at that and it tells me how much that falling edge. And if I look at the rising edge, then I trigger on the falling edge and go look. Okay, does everybody follow? It's a very practical problem. Yep, then you could trigger here. Yep, and then look over here as well. And then what would you do? You could put the scope on a histogram and get a distribution for the jitter. You could get a nice little probability, distribution. This is a very practical, very big deal. This is one of the reasons in some of the real high resolution data converters, they use laser triggers, because you can generate laser pulses with less jitter than you can a lot of times the electrical pulses. So this is not just applicable here, it's applicable in optics too when you're making measurements. Okay, but before we do that and we stop and take our grade booster, what I wanted to do just real quick is I want to point out why this is such a big deal. This is a huge deal in doing data converter design because your jitter is limits you, and that's one of the reasons why when we use oversampling, where you're sampling lots of pulses, which is what we're going to spend the remainder, which the delta sigma topologies, they average the clock pulses. And so when you average the clock pulses, sometimes a little early, sometimes it's a little late, your stability requirements in the clock jitter don't have to be as stringent. And so you can use a more jittery clock and still get good resolution. Okay, so look at this. And if you look, if I've got a sampling rate of 100 megahertz and a resolution of 6 bits for a half LSB uncertainty, My stability in my clock has to be 50 picoseconds. If I go up to 8, 12.5. If I go to 12, I'm at femtoseconds, 780 femtoseconds. Okay? Does everybody see this is like unrealistically good jitter? I mean, if you come to me and you say, I've got this integrated circuit that can generate a clock with one picosecond jitter, I'm going to be like, really? Show me, because your power supply, you basically look at your power supply and it's going to cause more than 1 picosecond jitter with noise. And then here's with 44.1 kilohertz. Why did I pick that one? Yeah, CD sampling frequency, what they store data on, which you all know now. Oh, why do they get so low? Only basically a little bit above twice the audio bandwidth. It's because they use all that compression, decimation and compression algorithms. And you can see if I'm going up here and I'm running the clocks at 44.1, even at 16 bits, which isn't that great for an audio DAC, it's okay. You need 110 femtoseconds or picoseconds of stability there for your jitter. But that's why when we go use the delta sigmas and we interpolate and raise the sampling frequency, then these numbers all get much better. They don't have to be as good because now I've got a higher sampling frequency and I'm averaging the clocks and it makes the distributions go down. One last thing related to this is, and you'll see this later, and I'll try to pick it up next time, but if you look at any probability density function, so this say is the jitter, we'll just say del TS, and it average is 0, but then it goes out here and it goes out here. I'm going to cover this more, but I want you to know, the filters we've been spending a lot of time on where we average K points. Okay, if the variance here is sigma, which is the mean squared value, okay, the standard deviation sigma, then this is the RMS value. When you run these random signals through one of your low-pass filters like this and you start averaging points, what it does to the spectrum is it makes of course the area has to be the same, but what it does, not to the spectrum, to the probability density function, is it reduces the distribution. And so your variance becomes sigma over K, and the RMS value becomes sigma over square root of K. And so that makes sense if my edges here is a little bit too early, but on the following it's a little bit too late, and then the next one it's right in the middle. When you average those points together, they tend to reduce the variation, and so you get a tighter distribution. And we're going to use this to get around a lot of these problems we're talking about, is averaging points so that we get less variation. So I'm just planting that seed in your brain. So if I use an average of clock signals over and over again, sometimes early, sometimes it's late, it tightens up the distribution by the number of points that I average. So if I use a really big K, I get a really tight distribution, like 1,000, and then my jitter becomes much less of a concern. All right, so we'll stop here. Is there enough information in today's lecture?